Let's begin our journey at the very start, the birth of the universe. Around 13.8 billion years ago, the universe began with the Big Bang, a moment of unimaginable energy and density. In an instant, space-time and matter all came into existence. The universe was incredibly hot and dense, filled with a soup of fundamental particles. As it expanded, it began to cool rapidly, setting the stage for everything that would follow. This expansion and cooling were crucial, as they allowed the first building blocks of matter to form. Understanding this moment helps us appreciate how the universe evolved from chaos into the structured cosmos we see today. Immediately after the Big Bang, the universe was a seething hot plasma, a dense soup of particles like protons, neutrons, electrons, and photons. Temperatures soared to billions of degrees, making it impossible for atoms to form. Instead, these particles zipped around at incredible speeds, constantly colliding and interacting. This early phase was chaotic, but it was also the foundation for everything to come. As the universe continued to expand, it began to cool and the energy levels dropped. This cooling was essential as it allowed the next steps in cosmic evolution to unfold. As the universe cooled further, about 1 second after the Big Bang, conditions allowed protons and neutrons to form from the sea of quarks and gluons. These particles are the building blocks of atomic nuclei. The balance between protons and neutrons was determined by the temperature and the laws of physics governing particle interactions. This delicate balance would later influence the types and amounts of elements that could form. The emergence of protons and neutrons marked a major milestone, setting the stage for the creation of the first atomic nuclei. Roughly 3 minutes after the Big Bang, the universe had cooled enough for protons and neutrons to start fusing together. This process, called nucleosynthesis, led to the creation of the first atomic nuclei. Most of the universe's hydrogen and helium formed during this brief window, along with trace amounts of lithium and beryllium. The conditions had to be just right. If the universe had cooled too quickly or too slowly, the abundance of elements would be very different. This era set the chemical foundation for all matter in the cosmos. During Big Bang nucleosynthesis, hydrogen became the most abundant element in the universe. Nearly 75% of all normal matter formed as hydrogen nuclei or protons. This overwhelming abundance of hydrogen would later fuel the formation of stars and galaxies. Hydrogen's simplicity made it the perfect building block for more complex elements, and its presence is still felt throughout the cosmos today. Without this initial surge of hydrogen, the universe as we know it would look very different. Alongside hydrogen, helium was the next most abundant element produced during nucleosynthesis. About 25% of the universe's normal matter became helium nuclei, each made of 2 protons and 2 neutrons. Helium's formation required precise conditions. Too many or too few neutrons would have changed the outcome. This helium would later play a crucial role in star formation and the evolution of galaxies. Its presence in the universe is a direct fingerprint of the Big Bang's early moments. While hydrogen and helium dominated, trace amounts of lithium and beryllium also formed during Big Bang nucleosynthesis. These elements were much rarer, making up only tiny fractions of the universe's matter. The conditions needed for their creation were even more delicate, and most of the lithium and beryllium that exists today was actually formed later in stars. Still, their presence provides important clues about the early universe and the processes that shaped it. During Big Bang nucleosynthesis, the universe was only able to produce light elements. Heavier elements like carbon, oxygen, and iron couldn't form because the universe cooled too quickly and lacked the necessary conditions. The process was simply too brief and the density too low for these complex nuclei to assemble. Instead, the creation of heavier elements would have to wait for the first stars, which would later forge them in their cores through nuclear fusion. After about 20 minutes, the universe had expanded and cooled to the point where nucleosynthesis could no longer continue. The temperature dropped too low for nuclear reactions to occur, freezing the relative abundances of hydrogen, helium, and trace elements. From this point on, the universe was left with its initial chemical makeup, which would remain largely unchanged until the first stars began to shine. This marked the end of the Big Bang nucleosynthesis era. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. This allowed light to travel freely for the first time, creating the cosmic microwave background (CMB). The CMB is a faint glow that fills the universe, providing a snapshot of the cosmos at this early stage. Studying the CMB gives scientists valuable information about the conditions of the early universe and the processes that shaped it. The formation of neutral atoms, the universe transitioned from being opaque to transparent. For this, photons were constantly scattered by free electrons, making it impossible for light to travel far. Once electrons joined with nuclei, photons could move freely, and the universe became transparent. This transition is what allowed the cosmic microwave background to be released, carrying information from the early universe across billions of years. Cosmic microwave background is one of the most important pieces of evidence for the Big Bang theory. It provides a direct glimpse into the universe's infancy, showing us what conditions were like just hundreds of thousands of years after the Big Bang. Tiny fluctuations in the CMB reveal information about the distribution of matter and energy, helping scientists understand how galaxies and large-scale structures form. The earliest moments, the universe contained nearly equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other, releasing energy. However, for reasons still not fully understood, tiny excessive matter remained after most of the annihilations. This leftover matter is what makes up everything we see today: stars, planets, and even ourselves. The mystery of why matter won out over antimatter remains one of the biggest questions in cosmology. Neutrinos are nearly massless particles that played a significant role in the early universe. They were produced in huge numbers during the first seconds after the Big Bang and interacted only weakly with other matter. Neutrinos helped shape the evolution of the universe by carrying away energy and influencing the formation of large-scale structures. Today they still zip through space, barely interacting with anything, but their presence is a key part of our cosmic history. From the moment of the Big Bang, the universe has been expanding and cooling. This expansion stretched space itself, causing temperatures and densities to drop over time. The cooling allowed particles to combine and form atoms and later molecules. This ongoing process continues today, with the universe still expanding at an accelerating rate. The interplay between expansion and cooling has shaped every stage of cosmic evolution. As the universe cooled further, electrons were able to combine with protons and neutrons to form the first atoms. Hydrogen atoms formed first, followed by helium. This process, known as recombination, was a major turning point. With atoms in place, the universe became transparent to light, and the stage was set for the formation of stars and galaxies. The creation of atoms was a key milestone in the universe's journey from chaos to order. After recombination, the universe entered a period known as the Dark Ages. During this time, there were no stars or galaxies, just vast clouds of hydrogen and helium atoms. The universe was dark, with no sources of light except the fading glow of the cosmic microwave background. This era lasted for hundreds of millions of years, until the first stars ignited and began to light up the cosmos. Even during the Dark Ages, gravity was at work. Tiny fluctuations in the density of matter began to grow under the influence of gravity, pulling atoms together into clumps. These clumps would eventually become the seeds of galaxies and stars. Gravity's relentless pull was the driving force that transformed a nearly uniform universe into one filled with structure and complexity. After hundreds of millions of years, the first stars began to form from collapsing clouds of hydrogen and helium. These stars, known as population III stars, were massive and short-lived. Their intense heat and light ended the Dark Ages, reionizing the universe and paving the way for the formation of galaxies. The birth of the first stars marked a new era in cosmic history. The first stars lighting up the universe, gravity continued to pull matter together, forming the earliest galaxies. These galaxies were the building blocks of the large-scale structures we see today. Over billions of years, galaxies merged and evolved, creating the diverse array of cosmic structures that fill the universe. The formation of galaxies was a direct result of the processes set in motion during the Big Bang and its aftermath. Dark matter, an invisible form of matter, played a crucial role in the formation of galaxies. Although we can't see it directly, its gravitational effects help pull ordinary matter together, speeding up the growth of cosmic structures. Without dark matter, galaxies might never have formed as they did. Its mysterious presence continues to puzzle scientists, but its impact on the universe is undeniable. As galaxies formed, they didn't remain isolated. Gravity pulled them together, causing them to merge and interact. These mergers were violent events, reshaping galaxies and triggering bursts of star formation. Over time, these interactions built up larger and more complex galaxies, setting the stage for the cosmic structures we observe today. The centers of many early galaxies, supermassive black holes, began to form. These cosmic giants grew by swallowing gas, dust, and even stars. Their immense gravity influenced the evolution of their host galaxies, shaping their structure and activity. The formation of supermassive black holes is still an area of active research, but their presence is a key feature of the universe's early history. While the Big Bang produced only light elements, the first stars began to forge heavier elements in their cores through nuclear fusion. When these stars died in spectacular explosions called supernovae, they scattered these elements into space. This process enriched the universe with the building blocks needed for planets and life. The cycle of star birth and death continues to shape the chemical makeup of the cosmos. Galaxies formed and merged, they began to arrange themselves into a vast cosmic web. This web is made up of filaments of galaxies and dark matter, separated by enormous voids. The cosmic web is the largest structure in the universe, and its formation was driven by gravity acting on tiny fluctuations in the early universe. Studying the cosmic web helps scientists understand how the universe evolved on the grandest scale. Cosmic inflation is a theory that proposes the universe underwent a rapid expansion in the first fractions of a second after the Big Bang. This inflation smoothed out the universe and created the tiny fluctuations that would later grow into galaxies and clusters. Inflation explains why the universe appears so uniform on large scales, while still containing the seeds of structure. Scientists have tested the Big Bang theory in many ways, including studying the cosmic microwave background, the abundance of light elements, and the large-scale structure of the universe. Each line of evidence supports the idea that the universe began with a hot, dense state and has been expanding ever since. Ongoing observations continue to refine our understanding of the universe's origins. One of the key discoveries supporting the Big Bang is the observation that galaxies are moving away from us, with more distant galaxies receding faster. This relationship, known as Hubble's law, shows that the universe is expanding. The expansion rate, called the Hubble constant, helps scientists estimate the age and size of the universe. This discovery was a turning point in cosmology. As the universe expands, the light from distant galaxies is stretched to longer, redder wavelengths, a phenomenon known as redshift. This effect is similar to the Doppler shift in sound waves. Redshift provides direct evidence for the expansion of the universe and allows astronomers to measure distances to faraway galaxies. It's a crucial tool for understanding cosmic history. By studying the expansion rate and the cosmic microwave background, scientists have determined that the universe is about 13.8 billion years old. This age fits well with observations of the oldest stars and galaxies. Knowing the universe's age helps us place other cosmic events in context and understand the timeline of cosmic evolution. The ultimate fate of the universe depends on its expansion rate and the amount of matter and energy it contains. Current evidence suggests that the universe will continue expanding forever, driven by a mysterious force called dark energy. Over trillions of years, galaxies will drift apart, stars will burn out, and the universe will become cold and dark. This scenario is known as the heat death of the universe. Modern observatories, both on Earth and in space, have revolutionized our understanding of the early universe. Telescopes like Hubble and observatories like the Planck satellite have provided detailed images and data on the cosmic microwave background, galaxy formation, and more. These tools allow scientists to peer back in time and study the universe's origins with unprecedented clarity. Computer simulations have become essential tools for understanding the early universe. By modeling the physics of the Big Bang, nucleosynthesis, and galaxy formation, scientists can test theories and compare results with observations. These simulations help reveal how tiny fluctuations grew into the vast cosmic structures we see today. Particle physics plays a crucial role in understanding the early universe. Experiments at particle accelerators like the Large Hadron Collider recreate conditions similar to those just after the Big Bang. These experiments help scientists study fundamental particles and forces, shedding light on how the universe's building blocks came together. Despite its importance, dark matter remains one of the universe's greatest mysteries. Scientists are searching for direct evidence of dark matter particles using underground detectors, space telescopes, and particle accelerators. Discovering the true nature of dark matter would revolutionize our understanding of the cosmos and its evolution. Dark energy is an even more mysterious force, driving the accelerated expansion of the universe. Its nature is unknown, but it makes up about 70% of the universe's total energy. Understanding dark energy is one of the biggest challenges in modern physics and cosmology, with profound implications for the fate of the universe. In addition to the cosmic microwave background, scientists have discovered other cosmic backgrounds, such as the cosmic neutrino background and the cosmic infrared background. These backgrounds provide additional clues about the universe's early history and the processes that shaped its evolution. Each background tells a different part of the cosmic story. Large-scale cosmic surveys map the distribution of galaxies and matter across the universe. These surveys help scientists test theories of cosmic evolution and understand how structures formed over billions of years. By combining data from many sources, researchers can build a detailed picture of the universe's history and its underlying laws. Quantum fluctuations in the very early universe seeded the tiny variations in density that would later grow into galaxies and clusters. These fluctuations were amplified by cosmic inflation, leaving imprints in the cosmic microwave background. Studying these imprints helps scientists understand the quantum origins of cosmic structure. Anthropic Principle suggests that the universe's physical laws and constants are finely tuned to allow for the existence of life. Some scientists argue that if the conditions during Big Bang nucleosynthesis had been even slightly different, life as we know it might not have been possible. This idea sparks debate about the nature of the universe and our place within it. Some theories propose that our universe is just one of many in a vast multiverse. Each universe could have different physical laws and constants, with only some capable of supporting life. The multiverse hypothesis is highly speculative, but it offers a possible explanation for the fine-tuning observed in our universe. Study of the early universe and Big Bang nucleosynthesis is a dynamic field, with new discoveries constantly reshaping our understanding. Scientists continue to ask big questions and seek answers through observation, experimentation, and theory. Each breakthrough brings us closer to unraveling the mysteries of our cosmic origins. Understanding the early universe and nucleosynthesis has had a profound impact on modern science. It has shaped fields like cosmology, particle physics, and astronomy, influencing everything from the search for dark matter to the study of exoplanets. The quest to understand our origins continues to inspire new generations of scientists. The story of the early universe is also the story of us. The atoms in our bodies were forged in the hearts of stars, and the elements that make up life were created in the aftermath of the Big Bang. By studying our cosmic origins, we gain a deeper appreciation for our place in the universe and the interconnectedness of all things. As we look to the future, the study of the early universe and Big Bang nucleosynthesis promises even more exciting discoveries. New telescopes, experiments, and theories will continue to push the boundaries of our knowledge. The journey to understand our cosmic origins is far from over, and each new insight brings us closer to answering the biggest questions about the universe and our place within it.